Hello everyone, this is Sihan Liu presenting you super non-singular decompositions of polynomials and their application to robustly learning low-degree PDFs. This is a joint work with Elias Diakonikolas, Daniel King, Vasilis Kontonis, and Nikos Zarafis. Let's begin with the basic definition of polynomial threshold functions. A degree D PTF is a Boolean function that returns the sign of some polynomial evaluated at the input. This is a fundamental mathematical object that has received a lot of research interest across various fields of theoretical computer science, including computational complexity theory and learning theory. In this talk, we focus on packed learning of degree D PTFs. In particular, we'll focus on the scenario where the marginal distribution is Gaussian and that a constant fraction of the training data may be adversarially corrupted. This particular type of corruption is known as the nasty noise or strong contamination model. Formally, a clean training set is first generated by a standard pack sample oracle. Then an adversary reads the dataset with full knowledge of our algorithm, can choose to replace at most absolute fraction of the data points. Let's briefly review the literature in pack learning of degree D PTFs. In the noiseless setting, the early work of Moss and Turan shows that the learning task can essentially be solved by a reduction to linear programming. When there is only adversarial label noise, or in the so-called agnostic learning setting, the work of Kalai, Cliven, Mansour, and Servadia shows that one can use L1 polynomial regression to obtain statistically optimal error. Nevertheless, the algorithm incurs an exponential runtime in the accuracy parameter. After that, substantial progress has been made in the special case of d equals to 1, which give rise to the family of linear threshold functions. Specifically, a series of work developed a polynomial time algorithm with optimal error up to some universal constant. For the case of d greater than 2, progress has been much slower. In fact, the only prior algorithmic work is due to Diakonikolas, Kane, and Stewart, which gave a polynomial time algorithm for general low-degree polynomials. However, the error guarantees of the algorithm deteriorate drastically as d increases. This then raises a natural question. Can we develop efficient algorithms for low-degree PTFs with error guarantees that qualitatively match that of the LTF? In this work, we answer the question affirmatively. In particular, for any constant degree d and some tunable small constant parameter c, the algorithm runs in polynomial time and has an error equals to epsilon plus opt to the power of 1 minus c times some constant that depends only on c and d. Whether it is possible to achieve OD opt or even O tilde d of opt has been left as an open question. Our overall plan is to use a powerful learning paradigm for agnostic learning LTF, known as localization. In particular, we'll first learn some candidate polynomial P that could classify most large margin points with nearly optimal error. Then, we'll condition on the small margin points to learn a new Boolean function and repeat the above process. This iteration will continue until all but about opt fraction of points are left. To ensure the success of localization, we need to make sure the conditional distribution satisfies two key properties. The concentration properties, which is key to the accuracy of the partial classifier learned, and the anti-concentration properties, which guarantee that the amount of small margin points will not be too large so that we make steady progress in each iteration in terms of the amount of unclassified points. To instantiate our plan, we need two technical ingredients. The first one is a novel variant of the classic perceptron algorithm, which can be used to robustly learn large margin PTF under much weaker concentration and anti-concentration assumptions. As it mainly follows from running the standard perceptron algorithm in tandem with spectrum-based outlier removal, we'll omit the discussion of its technical detail. The second ingredient is our main technical contribution. At a high level, it constructs partitions of the low margin area such that the conditional distributions maintain the desired concentration and anti-concentration properties. Since the argument for the two properties almost mirror each other, in the rest of the talk, we'll mainly focus on proving anti-concentration. We first give an example that shows why naive localization failed. Consider the polynomial p equals to x1 squared times x2 squared. In a naive localization procedure, we'll simply use rejection sampling to condition on the set px smaller than epsilon. Pictorially, it is easy to see that this set is approximately the union of two rectangles, one captured by the inequality x1 smaller than square root of epsilon, and the other captured by x2 smaller than square root of epsilon. Then we claim that the polynomial gx equals to x1 squared will have poor anti-concentration under the conditional distribution. Indeed, gx is small as long as x sits in the rectangle x1 smaller than square root of epsilon, which has constant probability mass under the conditional distribution. So, how can we overcome this barrier in the specific counterexample? Fortunately, this issue goes away if we partition the low margin area into axis-aligned rectangles and condition on each of the rectangles separately. In that way, the conditional distributions remains log concave and therefore enjoys anti-concentration. Then we can essentially run our margin perceptron algorithm on each of the conditional distributions separately and recurse from there. Interestingly, the simple solution also sheds light into our solution in more general cases. Formally, for any degree D polynomial P, we show that there exists an efficient algorithm that partitions its low margin area into at most poly D 1 over epsilon many regions, such that the standard Gaussian condition on each of these regions satisfies strong anti-concentration property. Combining this with the robust large margin perceptron algorithm then gives us a powerful localization-based algorithm, allowing us to prove our main algorithmic result. In the rest of the talk, we'll sketch the proof of this polynomial anti-concentration result. Let's first begin with an ideal scenario that hopefully conveys some of the most important ideas in our overall approach. Suppose that P decomposes as a small number of linear functions. In particular, let Q be some linear transformation that maps the n-dimensional input to an L-dimensional space of size OD of 1. We assume that P can be rewritten as a linear transformation Q composed with some low-dimensional polynomial H. We claim that one can simply then cut the low margin area of P into axis-aligned boxes in the output space of Q, and that gives a partition that preserves anti-concentration in the corresponding conditional distributions. The intuition is rather straightforward. Roughly, the Gaussian distribution transformed by Q yields some other Gaussian. Moreover, this is true even after coordinate-wise conditioning. Therefore, anti-concentration follows from log concavity of these conditional distributions. Of course, this linear decomposition of polynomial cannot always be true. However, what does turn out to be true is that low-degree polynomials can always be decomposed as polynomials that resemble linear transformations. In particular, we consider polynomial transformations such that the smallest singular value of the Jacobian matrix evaluated at a random vector following the Gaussian distribution is non-trivial with high probability. Formally, this notion of resemblance has been called non-singular polynomials and used in the work by Kane in 2012 in the construction of pseudo-random generator for polynomial threshold functions. Moreover, a polynomial time algorithm has been given in the same work that allow us to find these approximate non-singular decompositions of any low-degree polynomial. Intuitively, non-singular polynomial transformations are similar to linear transformations because a certain type of Taylor-style expansion. Let's consider this Taylor-style expansion near a center point x. Specifically, the expansion gives rise to a constant term, a linear term characterized by the Jacobian at x, and a higher order polynomial residual term. If I restrict the attention to the neighborhood around x of radius about delta square, the high order then becomes dominated by the linear term as long as the Jacobian is sufficiently non-singular. Hence, at least locally, the polynomial transformation will behave more or less like a non-singular linear transformation. So, is non-singular decomposition sufficient for us to establish the desired anti-concentration? Well, almost. For technical reasons, it turns out that we need an even stronger non-singularity notion, which we call super non-singularity. This notion of non-singularity requires not only the first-order derivatives, but all higher-order derivatives of the polynomial transformation to be non-singular as well. Assume that we can write P as the composition of a polynomial with a super non-singular transformation. Then we claim that a partition strategy similar to the linear case, where we carve the low margin area into an axis-aligned rectangle in the output space of the polynomial transformation, will give us the desired anti-concentration property. Fortunately, a super non-singular decomposition indeed exists for general low-degree polynomials, and the proof is pretty much identical to that of the original non-singular decomposition. Moreover, compared to the usual non-singular decomposition, super non-singular decomposition has a subtle extendability property. That is, for any polynomial p and a given sufficiently super non-singular q, it is possible to extend q into some other super non-singular polynomial transformation with a few more coordinates, such that p decomposes into a polynomial composed with the new larger super non-singular polynomial transformation. With this extendability property at our hands, we're finally ready to state the anti-concentration proof sketch. Let's first clear up some notations. We'll let Q be the super non-singular polynomial, R be some axis-aligned rectangle, and P be an arbitrary polynomial. Our goal is to show that P anti-concentrates under the standard Gaussian condition on Qx lies in the rectangle R. In the first step, we'll use the extendability property to extend Q into some larger super non-singular polynomial transformation Q bar, under which P decomposes. Then, we can show that Q bar is locally approximately linear due to its super non-singularity property. Consequently, the standard Gaussian transformed by Q bar will behave like a mixture of linearly transformed Gaussian, where each Gaussian component corresponds to some linear transformation that closely approximates the behavior of Q around some center X. Observe that any polynomial must anti-concentrate under the Gaussian distribution by the classic Hilbert-Wright theorem, condition on R, since the resulting distribution is just some other lower dimensional Gaussian. Finally, recall that P is roughly the same as Q bar composed with some low degree polynomial. Its anti-concentration property therefore follows. This completes the anti-concentration proof. In summary, this gives us a localization procedure for polynomial threshold function. Together with the robust margin perceptron algorithm, we're now capable of building an iterative algorithm for learning PTFs. This concludes the talk. Thank you for your time.